Welcome dear learners. We are continuing quantum chemistry and in this module we are focusing on second order perturbation theory. We previously learned the first order perturbation theory and their applications with examples, and in this module we are focusing on second order perturbation theory. The contents of the present module are perturbation theory, a brief introduction for the sake of convenience, then non-degenerate perturbation theory, second order perturbation theory, second order correction to energy and wave function, and finally degenerate perturbation theory. First of all, perturbation theory. Perturbation theory is an approximation method that describes a complex quantum mechanical system in terms of simpler system for which the exact solution is known. As we all aware, there are two important approximation methods in quantum mechanics. They are the variational principle and the perturbation theory. And perturbation theory deals with finding out a problem or solution to Schrodinger wave equation to a quantum mechanical system in terms of simpler problems which is already solved or established. However, in variation principle we are using trial wave functions to find out the upper bound of some ground state energy of the system, and it is based on variational principle. Here we are focusing perturbation theory, especially the second order perturbation. Prior to entering into second order perturbation, we are moving on to some basic concepts as a revision about the perturbation theory. Perturbation, as you are aware, it is small disturbance, and perturbation theory consists of a set of successive corrections to an unperturbed problem. That is, we must have an unperturbed problem and we have to give a series of corrections for energy as well as wave function. The series of corrections are first order, second order, third order and higher order corrections, and for convenience we are generally moving up to second order correction for energy as well as wave function. In non-degenerate perturbation theory, there is no degeneracy of eigenstate. It is very important. Non-degenerate perturbation theory is very popular compared with the degenerate perturbation theory. And in non-degenerate perturbation theory, the significance is because the perturbation treatment of degenerate and non-degenerate energy levels are quite different, or energy levels may differ. If some of the energy levels of the unperturbed system are degenerate, others may be non-degenerate. In non-degenerate perturbation theory, we shall consider perturbation on non-degenerate energy levels only. Second order perturbation theory. Perturbation theory consists of a set of successive corrections to an unperturbed problem. That is, we must have an unperturbed problem where we know completely the wave function as well as energy of the system. That is taken as the unperturbed problem. And to that unperturbed problem, we have to give a series of corrections. First order correction, first order, second order correction, so on so. And these series of corrections is applicable to energy as well as wave function of the unperturbed problem. In the second order perturbation, we are performing a second order correction to energy as well as wave function in succession to the first order correction. That is, in a second order correction, we have to consider the first order correction as well as the second order correction. Then we will get a more accurate result after the perturbation treatment. Now, we have to begin the second order perturbation theory. In order to illustrate the second order perturbation theory mathematically, we have to begin from the Schrodinger wave equation. We are having a quantum mechanical system where we are unable to solve the Schrodinger wave equation directly, and the Schrodinger wave equation to be solved is Hamiltonian psi is equal to energy into psi, where you are aware with the h hat H hat is called the Hamiltonian operator. Hamiltonian operator is otherwise known as the total energy operator. H hat comprised of two parts. H hat is equal to minus s cross square by 2m del square plus V. Del square plus V. V represents the potential energy part and minus s cross square by 2m del square represents the kinetic energy part. So, this is the Hamiltonian operator or total energy operator. Hamiltonian of psi is equal to energy into psi. This is an eigenvalue equation. That means whenever you are operating your wave function with the Hamiltonian operator, the result is the wave function back multiplied with the energy. So, this is an eigenvalue equation with eigenvalue equal to energy, and wave function can be considered as an eigenfunction of the Hamiltonian operator. Let this be the Schrodinger wave equation to be solved for the quantum mechanical system under consideration. And it should be noted that here the wave function or this equation, this eigenvalue equation, this Schrodinger equation contain no time variable. Hence, we are discussing time independent perturbation theory. So, we start from time independent Schrodinger wave equation. Finally, we are saying that this is the Schrodinger wave equation of the system to be solved, and the Hamiltonian H hat present in the system can be broken into two parts. The first part is H hat 0 and the second part is lambda H hat dash. As you are aware in previous modules, H hat 0 represents the unperturbed part and lambda H hat dash represents the perturbation. And for the sake of the convenience, lambda is taken as the perturbation parameter, and in many cases we take the perturbation parameter lambda is equal to unity. Thus, the first part of the perturbation treatment is that the Hamiltonian of the system to be break into two components. The first part is unperturbed Hamiltonian and the second part is the perturbation. Now, it is further assumed that the perturbation, that is lambda H hat dash, the perturbation is very less in magnitude compared with the unperturbed Hamiltonian, that is H hat 0, or simply lambda H hat dash less than H hat 0. And hence we can easily apply the perturbation theory to the present system. Associated with the unperturbed Hamiltonian H hat 0, there are a set of eigenvalues, and such eigenvalues are E10, E20, E30, etc. up to En0, where En0 represents energy after nth order correction. Corresponding to these eigenvalues, there must be eigenfunctions, and the eigenfunctions are represented as psi10, psi20, etc. up to psi n0. For instance, psi10 is the eigenfunction with energy value or with eigenvalue E10. Similarly, psi20 is the eigenfunction with the eigenvalue E20, and finally psi n0 is the eigenfunction corresponding to eigenvalue En0. Thus, we can write H hat psi n0 is equal to En0 psi n0. The eigenfunction psi n and the energy eigenvalues En of the total Hamiltonian H hat can be expressed as a power series of lambda. That means we can represent psi n and En as a power series in perturbation parameter lambda. Based on that, we can put psi n is equal to psi n0, lambda 1 psi n1, lambda 2, lambda square psi n2, lambda cube psi n cube, psi n raised to 3, etc. Finally, En is equal to En0 plus lambda raised to 1 En1, lambda square En2, lambda cube En3, etc. up to lambda n En raised to n. So, we can represent psi n as well as En as a power series in the perturbation parameter lambda. Now, on substituting equation, last mentioned equation 5 and 6 in the main equation Hamiltonian psi is equal to E psi, or the original Schrodinger equation Hamiltonian psi is equal to E psi, we get, after some mathematical rearrangement, we get a final solution we get a final simplified equation that is of the form h hat 0 minus en 0 into psi n 0 plus h hat dash psi n 0 plus h hat 0 psi n1 minus en1 psi n 0 minus en 0 psi n1 equal to 0. This is previously obtained from this lengthy equation, and on rearrangement of this lengthy equation we are getting equation 7, and equation 7 is obtained by putting equation 5 and 6 in the original equation, that is Hamiltonian psi is equal to E psi. Now we have to focus studiously on equation 7, and the coefficient of each power, first power of lambda, 0th power of lambda, second power of lambda, etc. There are coefficients in equation 7. So in equation 7, the coefficient of each power of lambda must vanish separately. That is, coefficient of first power must vanish separately, coefficient of second power, coefficient of third power if there, coefficient of 0th power, etc. to be vanished separately, such that based on this statement, the coefficient of each power of lambda must vanish separately. From equation 7, we can arrive at 3 important future equations. They are h hat 0 psi n 0 is equal to en 0 psi n 0, I mark it as equation 8. This is obtained by vanishing power of 0th lambda raised to 0, and this equation h hat dash psi n 0 plus h hat 0 psi n1 equal to en1 psi n 0 plus en 0 psi n1. This is obtained by vanishing the first power of coefficient of first power of lambda. Similarly, we got equation 10 by vanishing the coefficient of second power of lambda from the major equation 7, such that we got equation 10, which is h hat dash psi n1 plus h hat 0 psi n2 is equal to en2 psi n0 plus en1 psi n1 plus en0 psi n2. And it is clear that each term in equation 1 is having 0th power, each term in equation 9 having first power, each term in equation 10 have a second power. Since we are discussing with the second order perturbation theory, we have to begin from this mother equation, equation 10, that is the second order equation, that is h hat dash psi n1 plus h hat 0 psi n2 equal to en2 psi n0 plus en1 psi n1 plus en0 psi n2. And we have to take this equation, take the concept, applying the concept of the perturbation theory, and proceed to get the second order correction. Now we have this equation 10 with us, left multiplying equation 10 with psi n0. This term, bra and ket term, simply implies that you have to left multiply with the psi n0 star and integrate over space. And this is the command that indicates that you have to multiply each term in equation 10 with the psi n0 star and integrate over space. So this notation, this bra and ket notation simply indicates that, this part indicates that integral psi n0 star, and you have to integrate this function, and finally you have to put d2. So this is the procedure, and the unperturbed Hamiltonian is also having some Hermitian property. So by applying the Hermitian property of h hat 0 and by putting left multiplying with the psi n0 star and integrate over space, equation 10 can be suitably modified into equation 11. Equation 11 is an equation having 3 terms. LHS is an integral term. Right hand side also consists of 2 integral terms. Left hand side contain 1 Hamiltonian term also, and this is theoretically equal to integral psi n0 star h hat dash psi n on d2, and this part is en2 into integral psi n0 star psi n0 d2, and the last part is en1 into integral psi n0 star psi n1 d2, So, this equation 11 consists of 3 terms, one term on the left hand side and 2 terms on the right hand side. All terms are integral terms. The term on the left hand side consists of Hamiltonian operator also or perturbation also, since h hat dash is called the perturbation. We have the first order correction to wave function that we have previously learned. The expression for first order correction is there. Psi n1 is equal to summation prime m. There is an integral part, integral psi m0 h hat dash psi m d tau divided by en0 minus em0 into psi m0 d tau, and this equation gives the first order correction to the wave function. So, we already have the first order correction to wave function, and now we are proceeding with the second order correction, especially second order correction to energy. After the second order correction to energy, we can move on to second order correction to wave function also. Proceeding with the second order correction to energy, the concept on applying the concept of perturbation theory, we can simply reduce equation 11 to get En2 is equal to integral, this term is simply integral psi n0 star h hat dash psi n1 d tau. So, this is second order correction to energy. Substituting the value of psi n1, this we previously established in this equation. So, instead of psi n1, we have to put the value that we got previously. This is the value of psi n1. So, we have to put the value of psi n1 instead of this psi n1 in equation 12, and on proper rearrangement, equation the second order correction to energy can be get like this. This is summation term, this part is integral psi m0 h hat dash psi n multiplied with integral psi n0 h hat dash psi m, the whole divided by en0 minus em0. So, the second order correction to energy is represented by equation number 13. We know h hat dash is a Hermitian operator. What do you mean by the term Hermitian operator? An operator A hat is said to be Hermitian if it satisfies a mathematical condition. The mathematical condition is like this: integral psi I star A hat psi j d tau. This must be equal to integral psi j A hat psi I the whole star d tau. If an operator A hat satisfies this equation mathematically, then we can say that A hat is a Hermitian operator. And note the fact that h hat dash, that is the perturbation, is a Hermitian operator. So, based on that, we can arrive at this result, that is integral psi n0 h hat dash psi m d tau is equal to integral psi m0 star h hat psi n0 d tau. So, we can arrive at this conclusion based on the perturbation property of h hat dash, based on the Hermitian property of the perturbation h hat dash. Now, we get the second order correction in its final term like this: summation prime m integral psi m0 h hat dash psi n the whole square divided by en0 minus em0. This about the final second order correction to energy. The numerator of equation 12 previously we learned about 12, and that is a positive quantity. So, the sign of the correction term depends on definitely on the denominator, and we arrive at equation 14 basically started from equation 12. So, in equation 12 the numerator is positive. So, the sign of the entire function is governed by the parameters present in the denominator. So, sign of the denominator will give a sign of the correction. The second order correction to the energy level n due to energy levels for which En0 greater than Em0. If En0 greater than Em0, denominator will be positive. So, the second order correction to energy will be positive. If you are taking the reverse thing, that is En0 less than Em0, then denominator part will be negative and the second order correction will be negative. So, the sign of the second order correction exclusively determined by this denominator, that is En0 minus Em0. Now, we can also show some other relations. En3, this stands for third order correction. That is average of psi n0 h hat psi n2 and Enn is equal to psi n0 h hat psi n raised to n minus 1 d tau. This is or En raised to n is equal to integral psi n0 star h hat dash psi n raised to n minus 1 d tau. So, this expression, this is given in bracket notation, or we can put it in the integral notation also. So, if I am put it in the integral representation, En raised to n is equal to integral psi n 0 star h hat dash psi n raised to n minus 1, where n represents order of the correction, and that is the generalized equation for nth order correction to energy. From this is third order correction, this is nth order correction. From these equations, it can be shown that calculation of nth order energy requires a knowledge of n minus 1th order eigen functions. That is, to get fifth order correction, I must have the wave function corresponds to fourth order correction, or fourth order wave function correction is also required. This about the correction to energy. This is nth order correction to energy. Finally, saying nth order correction to energy requires the knowledge of n minus 1th order eigen function of the system under consideration. Now, since the contribution of second order, third order, etc. terms goes on successively decreasing, we primarily interested in the first order correction in many cases. The above statement, the above treatment is known as Rayleigh-Schrodinger perturbation theory. That is, according to Rayleigh-Schrodinger perturbation theory, we need not to consider corrections above second order, or we can stop nearly to the first order. This is because higher order corrections are successively decreasing, and we are especially focusing on the first order correction. This statement of simplification is known as Rayleigh-Schrodinger perturbation theory. We have now focusing on the second order correction to wave function. We discussed the second order correction to energy. Now we are giving prime focus to second order correction to wave function. In perturbation theory, we can give successive corrections to either wave function or energy, out of which we learned about the second order correction to energy, and now we are focusing the second order correction to wave function. We have the equation 10, that is h hat dash psi n1 plus h hat 0 psi n2 is equal to En2 psi n0, En1 psi n1, En0 psi n2, and the second order correction to the wave function is written as a linear combination of unperturbed wave function. Such linear combination of unperturbed wave function can be represented mathematically like this: psi n2, 2 for second order correction, summation k bk psi k raised to 0. And we have to substitute the value psi n2 in equation 2. Instead of this psi n2, we can put this expression psi n2 is equal to summation k bk psi k raised to 0. And we have to substitute this equation 15 in equation 10 and proceed mathematically like this. The result should be, on substitution of equation 15 in equation 10, you will get a result, and in each terms of that result, you have to left multiply with psi L0 star and integrate over space. On that mathematical proceeding, we will get this complicated integral equation, and this equation, in this equation, this lengthy equation, the first term on right side is equal to 0, and we have the first term on right is equal to 0, as well as on rearranging, we can simplify this equation by incorporating some constants like am, etc. And on rearranging this equation by putting the first term of the right hand side, that is this term, to be 0, and on rearranging, we will get BL into EL raised to 0 minus EN raised to 0 is equal to EN1 AL minus summation prime M AM integral psi L0 star h hat 0 psi M d tau. And for substituting different values of AL, we are getting, for substituting the values of AL and EN 1, that is first order correction to energy, we get this result for BL. That is BL is equal to summation m prime integral psi n0 h hat dash psi n d tau into integral psi L0 h hat dash psi m d tau divided by En0 minus Em0 into En0 minus El0. The entire thing minus integral psi n0 star h hat dash psi n d tau into integral psi L0 h hat dash psi n0 d tau divided by n0 minus L0 the whole square. This about the coefficient BL. By changing different values for L, we will get different values for BL. The normalization condition of the wave function shows that the coefficient Bn or coefficient Bn is equal to 0. It follows that the wave function of the system corrected to second order in the perturbation is psi n equal to psi n0 plus summation m am psi m0 plus summation m bl psi l0. The prime on the summation is again significance. Here there are two primes. That prime significance, the omission, the excluding of the states where m is equal to n and l is equal to n as the case may be. Now, we are moving to the last part of the discussion, that is nothing but degenerate perturbation theory. We previously mentioned about non-degenerate perturbation theory, where we are applying perturbation to non-degenerate eigenfunctions, and now we are focusing degenerate perturbation theory. We must emphasize here that the unperturbed wave function psi n0 is a unique one in the non-degenerate case. When there is degeneracy, that is more than one arrangement with the same energy, a linear combination of the degenerate wave function can be taken as the unperturbed wave function. For simplicity, we shall consider a case in which the unperturbed energy level En0 is twofold degenerate or doubly degenerate. It is an assumption. En0 is doubly degenerate. Then psi n0 and psi l1 are the eigenfunctions, and the linear combination can be represented as the wave function phi is equal to Cn psi n raised to 0, Cl psi l0. We have already this equation. This is equation 10, and based on the this is equation 9. H hat dash psi n0 plus h hat 0 psi n1 equal to En1 psi n0 plus En0 psi n1. And we can make some replacement instead of psi n0 with the phi. So, this equation changed it to this lengthy mathematical equation. I marked at equation number 2. This is obtained by simple substitution. Now, left multiplying this equation 2 with psi n0 star and integrate over space. Again, you are getting this equation, and h hat 0, the unperturbed Hamiltonian, is having Hermitian property. So, we can arrive at this result. Integral psi n0 star h hat 0 psi n1 d tau is equal to n0 into integral psi n0 star psi n1 d tau. Thus, this equation, this lengthy equation, can takes the symbol form h dash nn minus n1 into cn plus h dash hat nl cl is equal to 0. Operating equation 2 from left by psi n0, we are getting another equation, that is h dash lmcn plus h dash ll minus en1 into cl is equal to 0. So, we are getting two set of equations, equation 3 and 4. Equation 3 and 4 form a set of simultaneous equations, and for getting non-trivial solution, we have to represent it as a secular equation of the form, and the determinant represented here should be equal to 0. This is the condition for getting non-trivial solution to equation 3 and 4. This simply means that we clubbed equation 3 and 4 to get a new equation, and for getting the non-trivial solution, we are writing this matrix, this determinant is equal to 0. That is, determinant HNN dash minus ENN, HNL dash, HNL dash, HLL dash minus ENN is equal to 0. And this equation leads to two important solutions, and these are such solutions. En plus or minus 1 is equal to half into HNN dash plus HLL dash plus or minus half into HNN dash plus HLL dash the whole square plus 4 into modulus of HNL dash the entire raised to 1 by 2. Thus, we are getting two corrected energies, and the corrected energies are En equal to En0 plus En plus 1 and El is equal to En0 plus En minus 0. This is first order degenerate perturbation theory, and these are two set of energy values obtained after correction, and we assume here that our energy levels are doubly degenerate. So, I got two values for energy marked as En and El, and they are designated here. Now, En is equal to En0 plus En plus 1 and El is equal to En0 plus En minus L. Both the energies will be real since diagonal of the determinant matrix or determinant elements are real. If HNN dash equal to HLL dash and HNL dash is equal to 0, then we can say that En plus equal to En minus and the degeneracy not removed. That is, there are degeneracy will be 2, that is the system exists as a doubly degenerate system. Now, the normalization condition enable the calculation of the coefficients Cn and Cl, which again give desired linear combination associated with both the energy values. The energy values for a doubly degenerate system are En0 plus En plus 1 and En0 plus En minus 1. Here En0 represents the energy of the unperturbed system. Thus, we have discussed second order perturbation theory, second order correction to energy, second order correction to wave function, and also about degenerate perturbation theory. Have a nice learning experience. Thank you.